Welcome back everyone. In this lecture we will begin with basic notions from graph theory. So, we will define what are the graphs, and then later we will see some basic examples like cycles, trees and characterizations of them and so on. So, let me actually briefly explain the history of graph theory. So, in 1736 Euler actually wrote this fantastic paper that actually addresses the 7 bridges of Konisberg problem. So, this problem was asked by the king who was ruling at that time. So, here is the map of this Konisberg that is plotted in 1651. So, it is a rough map that I have actually tried to draw it here. So, here these yellow line this blue lines, so that is the river that was actually passing there, and these red lines, they are actually the bridges that were actually built on this river belt. So, now so the 7 bridge problem or 7 bridges of this Konisberg problem, which actually asks the following question. So, look at this 7 bridges in this map. Okay. So, it asks the following question. So, can we devise a walk through the city that would actually cross each of those 7 bridges once and only once? So, this is the question that was asked. So, of course, those days the military, the infantry actually they all go by walk and so on, or use horses. So, crossing these bridges and all like a very important thing. So, somewhat related to that, the king of those days, he wondered whether one can actually devise a walk through the cities. So, that would actually cross each of those bridges once and only once. So, now if you think abstractly, so basically we have these 4 part of the lands, which I have actually labeled them as this M, which is the middle land, and then this upper left hand and the lower left hand land, and then this right land. So, these are all of them are land, okay, and these blue lines, like I said, that is the river that passes there, and these red lines, they denote these bridges that we are interested in. But as far as crossing the bridge concerned, the walk that we are actually going to do in the cities, that actually not going to be counted. So, one can actually rewrite this 7 bridge problem in more abstract terms by introducing what is called graphs. So, in order to do that, what we will do, we will just denote this each land mass as vertices. So, these whatever that M, R, UL, LL that I have denoted. So, these are all like land only. Okay. So, those things I just denote them as vertices. So, then the bridges we just denote them as edges. For example, if we take this M, this is a vertex, and then this UL, this is also vertex. So, then we have indeed two edges between them, and both actually given by these 2 bridges between UL and M. Okay. So, I guess the construction is very clear. So, we are turning this real life problem into an abstract mathematical problem by replacing the land pieces by vertices and the bridges by edges. So, now you can see that there are these 5 bridges are connected with this middle land M. So, that means that vertex should have degree phi. Okay, there are 5 edges actually comes from that middle land M. Similarly, UL and LL 3 edges comes out, and R has 3 edges adjacent to that. Okay. So, the real life problem now converted into somewhat graph theory problem. So, now we can actually ask the following question. Now, this devising a walk through the city that satisfying this condition is same as we just walk between the vertices. Okay, we start with, for example, M and then go to UL and then go to R and come to LL like that. But the question it's asked, you just walk like this between the vertices, but then you need to actually cross each bridge only once. Okay. So, you have to cross every bridge and only once you have to cross. So, if we try to do this, actually we can prove using graph theory that it is not possible. So, the answer to this 7 bridges of Konisberg problem is actually negative. So, Euler proved that it is impossible to do impossible to get such a walk. So, we will see proof of this later in this course, but this already kind of motivates us like where the graphs are indeed coming from. So, now if we think about it, we can actually look at such real life problems, for example, like problem of where to have towers, mobile towers, and how many roads like we need to make between the cities, so that actually kind of minimizes the construction value and so on. So, all those problems can be converted into problems about graphs. And so, even in modern mathematics like even in machine learning and so on, so graph theory is actually inevitable. So, they are all used everywhere. Okay. So, what I plan to do in this few lectures, maybe 1 or 2 hours lectures, that I want to just introduce basic graph theory and then some basic terminologies that are used in graph theory. So, let us start with the basic definitions and then we will build from there. Okay. So, we will begin with the definition of graphs. So, we tried to be tried to include some more general notion of graphs. So, in particularly we would like to include loops and multiple edges and so on. So, for that purpose what we are going to do, we will actually define a graph to be an ordered triple. So, we denote graph to be G and then this is given to be an ordered triple, which consisting of the set of vertices, the set of edges and this incidence function called psi g. So, here as I told this V of G, this is the set of vertices and this E of G, they are the set of edges and this is the incidence function. So, now we assume that V of G is disjoint from E of G. So, from the set theory point of view, these two are two disjoint sets, that is important. And this incidence function, what it does, so if E is an edge and U and V are vertices of that edge, so then this incidence function takes E to U V. So, this psi g, it is a function from E of G to some multi sets of V G. So, let me actually just write it as P 2 of V G and then I will explain what is this P 2 of V G. So, basically given E, we assign this to unordered tuple uv. So, we denote, so basically from the pictorial point of view, an edge will look like this. So, this is an edge between the vertices u and v. So, then the incident function takes psi g of E to this u v. So, if you are not comfortable with this notation, this is same as the unordered tuple u v. So, what is my P 2 of v? So, P 2 of v it consisting of all 2 element sets, multi sets, where the elements are actually coming from this capital V. So, you take all possible u comma v, it is an unordered tuple u comma v, where u and v it comes from this capital V. So, now it can happen that u could be equal to v. In that case, we are considering the multiset u comma u. So, indeed that corresponds to the loop in the graph. Okay. So, there is no restriction on this. So, this is indeed could be multiset, could be multiset like u comma u. So, this is the convention. So, this incident function assigns for each edge E obtained from joining u and v. So, that is what this incident function actually records. The vertices u and v are called the ends of E or end points of E. So, this is the very general notion of graph. So, now this for example includes all the graph that contains loops and multiple edges and so on. Okay. So, let us see some example, then it will become very clear. So, let us look at a graph that consisting of 5 vertices. So, V of g is given by V1, V2, V3, V4, V5, and then E of g is let us say 8 edges E1, E2, E3, E4, E5, E6, E7 and E8. So, what we are doing? So, now we need to say what are all the end points of each edge E1 etc. E8. So, that is defined by, so basically the incident function is defined by, so you take the end points of E1 to be V1, V2 and psi g of E2 to be V2, V3 and so on, and psi g of E8 is given by V2, V5. So, let me draw this graph explicitly. So, then it becomes clear like what we are actually doing. So, I have these 8 vertices. So, V1, V2, V3, V4, V5, V6, V7, V8. So, now E1 connects this V1, V2. So, this is my E1, and then we have V2, V3, that is E2. So, this is E2, and what is E3, which is V3, V3. So, I will take this this to be my E3. And then we have V3, V4. So, that is my E4. So, the E8 is nothing but V2, V5. So, this is my E8. So, like that I am drawing the graph. Is E8. So, what is E5? V2, V4, we take it to be E5. This is E5, and then E6, V4, V5. E7 is V2 V5. So, that means I am allowing multiple edges. This is my E7. So, note that this is indeed a disconnected graph which has four different components, and it is clear that, for example, E7, E8 both are actually edges between V2 and V5. So, this is V2 V5 and this is also V2 V5. So, we are indeed like as sets, if you want to record. So, you record them as multi 2 sets. So, this V2 V5, this is my E7, and then E8 is again V2 V5. So, that is why this incident function is very important. So, which helps us to actually record both loops as well as multiple edges in more clean way. Okay, so this is actually defines mathematically what is the graph. So, now one can actually use vertices and edges in order to draw the graph in any plane. That is the most of the pictorial interpretation that we use while working with the graphs. So, but the way we draw the graph that may actually can differ, but still it may give us same information that one needs to actually define the graph. For example, one can simply take graph something like this. Okay, let us say 1, 2, 3, 4, and then you have these E1, E2, E3, E4. So, this same graph can be drawn as follows. So, you draw like this. So, now instead of connecting 1, 3, so this is same as 1, 2, 3, 4. So, 1, 3 is connected and then 2, 4 is connected and 1, 2 and 3, 4 are connected. So, indeed these graphs are same graphs only. This is E1 and this is E3, this is E2 and this is E4, but we have two different ways to draw the same graph. But we need to actually convince ourselves that they are same objects, that means they are isomorphic object. So, this motivates us to define isomorphism between graphs. So, we can actually define the following terminologies. So, we call two graphs are identical if the vertex set and edge set and incident functions, they are all same. And we can also define what is called isomorphism. So, isomorphism is slightly different from actually the graphs being identical, because the labeling of these vertices can be changed. So, instead of using E1, E2, E3, E4, I can also use E1 dash, E2 dash and E3 dash, E4 dash. Similarly, 1 dash, 2 dash, 3 dash, 4 dash we can use. But as far as the graph concerned, the information is same. So, we want to say that these two are isomorphic. Okay, so, let us first define what is identical graphs. So, we take two graphs G and H and we say that they are identical if all the information that used in the definition of the graph, they are same. That means G should be equal to H. So, which is equivalent to saying V of G is same as V of H and E of G is same as E of H and this psi G is same as psi H. Okay. In this case, we say that these two graphs are identical. So, now what is an isomorphism? And we want to call two graphs isomorphic, and so since only the labelings are differing and the adjacency is preserved. So, basically we need bijections between the vertices and edge sets, so that the adjacency in one first graph is preserved in the, like when you apply the map, it should be preserved in the another graph. So, let us make it very precise. So, let us say we have two graphs G and H, and we say they are isomorphic if there is, they are said to be isomorphic if there exist bijections, let us say theta from Vg to Vh. So, they are should be bijectively correspondent. Basically, we are changing the labeling, and there is another bijection from the edges to edges of H, edges of G to edges of H, such that, so whenever U and V are adjacent in G, so with respect to the edge E, that means psi G of E equal to UV. So, UV joined by an edge E, that is what it means, if and only if look at their images inside H. So, you have psi H of pi of E, and this pi theta of U and theta of V must be actually joined by pi of E. So, that is what we expect. Okay. Such a pair theta pi of mapping is called an isomorphism between G and H, and if you get this isomorphism map, then you call the G and H are isomorphic. So, the isomorphism consisting of a tuple theta pi satisfying this condition star, satisfying star is called an isomorphism. Okay, if there exists isomorphism, then you call that G and H are isomorphic. So, it is not difficult to actually see two graphs are isomorphic or not in some smaller graphs, so when the vertices are really small. But this problem determining given two graphs are isomorphic or not becomes very difficult problem when the graph actually grows really big, like the number of edges and number of vertices, if they are really large, then this problem is actually a very hard problem to decide given graphs are isomorphic or not. And this problem like studied both in mathematics as well as in computer science. There are nice algorithms that actually determines whether given two graphs are isomorphic or not. Anyway, we will not discuss this more in this course. So, the notion of isomorphism is what I wanted to discuss. So, now we are going to see some special classes of graphs which are important and they appear everywhere. So, first we will define the notion of simple graph, which is again very important when it comes to vertex coloring and so on. So, what is simple graph? So, a graph is called simple if it contains no loops and multiple edges. Okay. So, a graph G is called simple if G has no loops or multiple edges. So, it is very clear. So, what this means, for example, loop is something looks like this. So, this is something should not appear, and similarly one should not have multiple edges like this between U and V, E, F, T. So, this also should not happen. So, it is easier to write down in terms of words what is the meaning of simple graphs. Okay. So, now some special family of families of graphs that actually play important role in graph theory. let me just introduce them. So there is notion of this path, which is we denote it by Pn. So which is a graph which looks like this. You take the vertices to be 1 to n, and then you join I and I plus 1 vertex in the graph. So this is called path Pn. So the edges are labeled like E1, E2, etc., En minus 1. But anyway, so it's important to actually tell which vertices are actually adjacent in the simple graph. So in the definition of simple graph, we haven't allowed loops and multiple edges. So that tells us that if we actually take an edge, the edge is determined by its endpoints. So that means instead of actually just telling what are all the edges, it is enough to specify these two sets which comes from the power set of V, okay, and which are adjacent in the graph. So basically an edge in a simple graph determined by the endpoints. So that's why if we want to actually give examples of simple graph, it is enough to actually say which vertices are actually connected. So that can be recorded by putting and drawing a line between them. So for example, in this case, I don't need to actually tell what are all the edges, because we have already told by drawing this diagram I and I plus 1. So this is going to be the edge for I coming from 1 to n minus 1. Okay, so this is one important family of simple graph. So similar to this, we have what is called cycle graph. So cycle graph, which is denoted by Cn, which is just drawn as follows. You take n number of vertices and then consider some figure which is similar to n-gon. So 1, 2, 3, some k, n and n minus 1. So it's 4 actually. So basically what we are doing, we are actually adding an edge between I and I plus 1, and we do it modulo n. So all these edges which are there, I plus 1, where I coming from 1 to n minus 1, and then union you have this extra edge 1n. So these are all the edges of cyclic graph. Okay, so now we also have this notion of complete graph. So whenever we talk about complete graph, it is actually a simple graph that has the following property, which is usually denoted by Kn. So complete graph on n vertices, which is denoted by Kn. So what we do, we just join any two vertices among this 1 to n. So then so that produces a graph that we call it as complete graph. So what is the vertex set of Kn? It is 1 to n, all the vertices from 1 to n, and then the edge set is you connect any two edges where I is different from j coming from 1 to n. Okay. So that is actually called the complete graph on n vertices. For example, when n equal to 5, what we have is this. We have 5 vertices, let's draw like this, and then we need to just connect all of them. So for example, let's orient 1, 2, 3, 4, 5. These are all the vertices. So now what you do, you just join, one is joined with 2, 3, 4, 5, and then 2 is joined with 1, 3, 4 and 5. Similarly 3 is joined with 2, 1, 4 and 5, and then 5 is joined with this. Okay. So this is what called K5, complete graph of size 5. So, one can also talk about an empty graph. So, that is the graph that actually has no edges. So, actually the depending upon the size of the vertices. Okay. So, usually there is no notation actually used for the empty graph or the trivial graph. So, one can talk about graph having no edges, that we just simply call it as empty graph or a trivial graph. Okay. So, now there is this another important notion called bipartite graph. So, for that first we need to actually define what is called bipartition. So, a bipartition of the graph is a tuple x and y, where x and y are two subsets of the vertices, such that so each edge has one end in x and one end in y. So, you take the vertices of G and then you partition this into two sets, call it x and y. So, in the graphical notation it will be x and then this will be y, and any edge that actually comes from G. So, any edge comes from G will have one end in x and then another end in y. So, that is what called bipartition of given graph, and if you have a bipartition, then you call that graph as bipartite graph. So, a bipartite graph is a graph that has a bipartition. Okay. So, this is the important thing. So, again we allow bipartite graph to have multiple edges and all, that is not a problem. So, what is a complete bipartite graph? A complete bipartite graph, to begin with, it is a simple bipartite graph with the bipartition, let us say x and y, in which each vertex of x is joined to each vertex of y. So, let us write down. Usually we denote complete bipartite graph by k m comma n, where m stands for the number of vertices in x and n stands for the number of vertices in y. So, this is our complete bipartite graph. So, how it is defined? You have x here and then you have y here. So, now each vertex of x, it is actually joined to each vertex of y. So, let us say you have some 3 vertices here, then all of them joined, and then we are assuming it to be simple graph. Okay. So, that means either edge is there or not there, and all of them. So, let us say cardinality of x equal to 2 and then cardinality of y equal to 3, then we have something like this, and this is called complete bipartite graph of size 2 comma 3. Okay. So, again it is an important problem to actually determine a given graph is complete bipartite graph or bipartite graph or not. Okay. We will see some characterization how to determine a given graph is bipartite graph or not. Okay. I will stop here.